Hi there, welcome back to the Formulaic Approach channel. In this video we are going to talk about the spectroscopy of organic compounds. Now spectroscopy is one of the techniques in analytical chemistry that we use to determine investigate actually the effect of light on chemical substances, chemicals basically. So we use spectroscopy to observe the interaction between light and molecules. Is that okay? So as you already know, or as you should already know, that light is one of the electromagnetic wave spectrum. We have, and I've covered this in my previous physics videos, the electromagnetic wave spectrum. We have the radio, infrared, visible light, ultraviolet, X-ray and gamma ray. But in today's video we'll be majoring on the spectroscopy of these three bands, okay? Even though those are not the only spectroscopic techniques used, okay? So first, in order to understand spectroscopy of these organic compounds, we have to understand the following. We have to understand the energy of organic molecules, okay? So then we'll now talk about the interaction of organic molecules with light, okay? Then before we now talk about the spectrum and how it works, the spectrum, and then we'll now talk about the types, okay? Now once you understand these three, then you understand what we want to talk about under the spectroscopy. There are two types of spectroscopy that I said we'll be talking about. Okay, so let's first talk about the energy of molecules. Now, molecules have three types of energy, okay? And those are the electronic energy, and the electronic energy is basically, of course, in an atom there is going to be what? Electrons in atomic orbitals that are moving around, right? And the orbital that an electron exists is depends on the energy of the electron, right? So that high energy electron will be found in high energy levels or orbitals. Does that make sense? So the higher the orbital, the higher the energy. So it means that organic compounds have what? Electronic energy. So the first is energy, like I said. So we have electronic energy, which is energy of electrons in the orbitals. Then the second is the vibrational energy. The vibrational energy. Now, what is the vibrational energy talking about? The vibrational energy is about the vibration that occurs within the bond that holds atoms together. Okay, so practically speaking, we usually, it's in order to be able to visualize this vibrational energy, chemists usually like to represent molecules, such as, for example, water. Now, I want to use the bond on molecules. They usually use, they prefer to use this thing, springs, to act as if the bond between the molecules or the atoms there were like a spring, so that it can vibrate, because the atoms rather are necessarily vibrating on that bond. Is that okay? They are vibrating on that bond. Okay, so they possess vibrational energy. And the third, they possess rotational energy. Rotational energy. So this one is for electrons, this one is for the bond. The rotation is also for the bond, but it talks about how that atoms are able to, rotate about their fixed point or axis of the atom itself. So it can rotate on the bond about its axis, okay, an atom. All right, so these are the three energies. So it means that the total energy in a system, in a molecule, the total energy in a molecule is going to be total energy E, let's say E sub T, is going to be what? Energy due to electronic energy plus the vibrational energy plus the rotational energy. So this is going to be all the energy that you find, total energy that you find in an organic compound or any molecule at that. Okay, by the way, keep in mind that spectroscopy can be used for any chemical substance. Okay, I have talked about spectrophotometer before, spectrophotometry. Okay, so we can use, but I'm basically talking about the organic compounds today. All right, now let's talk about the interaction of organic molecules with light. Okay, now when light is made to pass through an organic molecule or an organic compound, now the electrons that make up that organic compound are going to absorb some energy, and that energy is going to cause them to vibrate. Okay, first is going to make them first to move from their position of stability, so they will move from a stable orbital to an unstable orbital. Okay, and they are able to do so because they have absorbed energy from the light. Okay, so it means you have to understand how the light works here. Now, in 1904, Albert Einstein said that light actually travels in small packets. I actually have a video on that explains that in physics. So you should do well to watch that video. I explained a lot about this. Now, I said that according to him, light actually travels in small packets of energy. Okay, so and those small packets of light are called photons. Okay, and the energy they carried called quanta here. So what that tells us is that the energy in a given photon of light, or the energy that these electrons actually get from that photon of light that touches them, is quantized. It's not a continuum. It's not a continuum. It's not continuous. Okay, not a continuum means this. So if this is a story building, if in a story building we have this the upper floor, this is the lower floor. Now, if you want to move to the upper floor to the lower floor, what you use is a ladder. Yeah, you use a ladder. Okay, but as opposed to look at this other side. So if you want to move from here to here, now you know it is almost impossible because except if friction were available, you will not be able to move up here, right? This is a continuum, right? This is a continuum. This is what we call, or is continuous here. This one, before you can move, if the height of each of these of this ladder staircase is about 20 centimeter, for example. So it means that every time you carry your leg or you lift your leg, you move 20 centimeter upward, right? 20. So the same way, energy that the electrons take is also quantized. That is, there's a particular amount they take each time they are able to move from a stable orbital to an unstable orbital or a higher orbital. So basically, it requires energy to delocalize electron. That's what I'm saying. So as you move up like that, you know, and what that means is that if the electrons do not get the amount of energy that they need, they will not move from that stable orbital to an unstable orbital. Okay, I've already explained this before in my video in physics. So just check one of my videos on absorptivity and reflectivity and all of that of in light waves. Okay, so I said that the electrons, if light that does not give them the amount of energy that they require, keeping in mind that the photon that this photon that I'm talking about right now is also quantized. It has an amount of energy, or it packages. It's in a packet of energy also, and it has an amount that it carries. So given that fact, if that energy is not equal to the amount of energy it needs to get to the next orbital that it wants to move to, or is not equal to the energy difference between its stable state and this unstable state that it wants to move to, the energy difference, if that packet is not up to it, what it will do is that it will give back that energy. The electron will not take up that energy. Does that make sense to you now? So it's just like, let me use the analogy of here in this part of the world. So if a child is told to bring something from school, let's say money, for example, and is told to bring 1,000 naira, Now, if you give the child 500 naira, what we'll do is that he will keep waiting and you until you give him that 1,000 naira before he goes to school. Do you understand? So it means that the electron will not, and the only difference with my analogy, or the defect in my analogy, is that the child will hold on to the 500 naira. In the case of electrons, they will not hold up to the energy that is not up to the energy difference between their stable orbital and their unstable level they are moving to. Does that make sense now? Okay, so what that means is that each electron will absorb a particular or a specific wavelength of light that has the same amount of energy as the energy difference between the unstable orbital, the stable orbital it is in, from which it wants to move to an unstable orbital by the taking up of that energy. Now, this effect is actually momentary, because so that you don't begin to think that will it stay in that unstable orbital. No, it will still relax back. Only that during that time when that light is incident on it, is going to move. There's going to be an energy that the electrons will, interact, light in which the electron will interact with by absorbing the energy. Okay, so that is about the interaction of light with the EM wave. Now let's talk about spectrum. Now you see, for the machine that is used to study spectroscopy is called, one is called the spectrophotometer, another is called spectrometer. So actually, from my findings, spectrophotometer are just other types of spectrometers. Is that okay? So I'll just say a spectrometer. Is that okay? So a spectrometer is used to study spectroscopy. Now, this spectrometer actually studies the absorptivity of the chemical. What do I mean by absorptivity? We have absorptivity and transmittance. Absorption and transmittance occur when light touches chemical. Okay, so absorption and transmittance. So now it studies how much light it absorbs and how much light it gives off. Okay, now let me quickly take you through how the process is. Now in that machine there is something called a cuvette. Now that cuvette is just a small tube, Now, there is a frosted side and there is a clear side. So when you put in your liquid, your chemical, okay, now there are two types of chemical you want to use. There is a chemical in which your chemical will be dissolved. That chemical, it could be water in this case. It's going to be called your blank. So we are going to have your blank and your actual chemical, your sample, okay, which will be your sample. So now, when you put the blank in the system, you set it to 100% transmittance. Now, here's what that means. When you set your transmittance to 100%, when you set the transmittance to 100%, it tells the machine that this material, this blank, which is our chemical in which this guy is dissolved, this guy is allowing 100% of light to pass through. Okay, even though all substances have their own absorptivity, degree of absorptivity, but you have set it so that it will take this as your blank. So by the time you're adding the chemical, it's going to now record the amount of light. So if you set it at 100%, after adding the chemical, by the time you fix it back and the light passes through the clear side, this chemical is going to reduce the amount of light that will be transmitted to a digital display. So let's say it records this now as 80%. It means that 20% of that light has been absorbed. Okay, 20% absorption has taken place, and so it's going to record its transmittance at 80%. So what it is able to do, the machine, the spectrometer is able to do, is now that it gives you your digital display a graphical what's it called now, representation of the absorption to the wavelength of the light, that sometimes frequency also. Okay, gives you a graph of the absorption that took place and the wavelength against the wavelength of light that came into the chemical. Okay, so and this graph is usually unique for every organic compound. Is usually unique. Okay, and so we call it fingerprints. Is that okay? We call it fingerprints. And what do I mean by fingerprints? Okay, now for humans, our fingerprints are very unique. Okay, so this graph also, since it's very unique for every organic chemical, is going to be the compound's fingerprints. Okay, so actually the one we basically call the organic chemical fingerprint or so is the IR spectroscopy. So we're going to get to that. So but let me reiterate what I said. I talked about energy of molecules, where there is going to absorption of light and then an electron will move to another energy level. Then there is when it moves to another energy level, the process is actually called electron transition or electronic transition. Okay, when it moves from stable to unstable orbital. Okay, and then there is interaction when you put when light is incident on it. Okay, such that it absorbs some and what transmits another. Okay, so and by absorption, the absorption is what causes the energy that the electrons actually take. Is that okay? Then the spectrum is where the spectroscopy is able to be able to digitally display the relationship between the absorbance and transmittance. Actually, you can now mathematically calculate things, maybe the intensity of the light and all of those things, using what we call the Beer-Lambert's law. Beer-Lambert's law. Okay, I think it's absorption is equal to B. Okay, I already made a video some 3 years ago on this. Okay, so that's just it. You don't need to even know how to do the calculation. Just understand this. Now let's talk about the two types of spectrometer. The types that I want to talk about. The two types of spectroscopy rather. The first one is the ultraviolet UV visible spectroscopy. That's what we call it. Now, UV visible spectroscopy has to do with the ultraviolet ray and what visible light spectrum. Okay, the ultraviolet ray and visible light spectrum. The visible light spectrum is from the ultraviolet rays from about 10 nanometers to 400 nanometers, while the visible light is from 400 nanometers to about 700 nanometers in wavelength. Okay, so now in the UV spectrometry, it is usually used to measure the absorption of UV visible or UV ray or visible ray that a molecule or that a chemical exhibits. Okay, how much of UV or visible spectrometry how much visible ray it absorbs. Okay, now this is the case. It is such that now this one is particularly used for conjugated systems. Okay, systems that have double bond or double bond or conjugated triple bonds or conjugated double bond system. Okay, now the reason is because most organic compounds, not all organic compounds rather, actually absorb a lot or significantly a lot from this band. Okay, between these 10 nanometer to 700 nanometer. Most of them actually absorb more from the infrared spectrum, and I'm going to show us that in a jiffy. But this is the idea. So with the conjugated with the alkenes, basically alkenes, for example, they absorb from the spectrum. And I've told you about the types of alkene. We have cumulated alkene, we have conjugated alkene. I'm going to talking about the conjugated alkene. It is such that, or chemists found out that the more the conjugation or the more the number of double bonds that a system has, the more of the UV spectrum it absorbs. Okay, so it absorbs higher wavelength of this UV visible light. Now, let me use 3 or 4 alkenes, for example. So, for example, ethene absorb a wavelength of about 1.65 times 10 raised to the power minus 4 centimeters. But you now see butadiene. You know, ethene has double bond like this, yeah? But look at butadiene has 1, 2, 1, 1, 2, 1. So this is 1, 2, 3, 4, okay. So you are going to see that this one is conjugated. Why? Because there is double bond. Conjugated system is one that has double and single bond following each other. So double bond, single bond, like that. Okay. So the next type. So this one actually is able to absorb at about 2.17 times 10 raised to the power minus 4 centimeters. Okay. While the hexatriene is one such alkene that is able to absorb about 2.58 times 10 raised to the power minus 4 centimeter wavelength. And carotene, you know that hexene has one double bond. This one has two double bonds from what I drew there. Hexatriene is going to have what? 3 double bonds. Carotene actually has 11 double bonds. Carotene, okay. So, and carotene is able to absorb at about 4.5 times 10 to the power minus 4 centimeter of wavelength. So what did you notice? You notice that as the conjugation is increasing, the wavelength that is absorbed is actually called H max, lambda max rather, not H max. The amount of wavelength that is able to absorb is what? Called lambda max. Okay, so the lambda max keeps increasing as the conjugation is increasing. Okay, so that's why UVVs is specifically used for conjugated system, whether ring, whether aromatic or aliphatic system. Okay, is best for it. All right, then the second type of spectroscopy that I will talk about. I will not talk about the NMR in this video. That's the nuclear magnetic resonance spectroscopy. I'll just be talking about the UV and the IR spectroscopy. IR stands for what? Infrared, right? Below red. Infrared spectroscopy. Now, spectroscopy. Okay, its own wavelength is about 700 nanometers, so about 1 millimeter. Okay, now one thing with this guy is that most of organic compounds actually are able to absorb within this spectrum, most of them. So that's why this one is not very reliable. It's not reliable for systems that are not conjugated or that don't have double bonds. What do you call them? Alkanes. It's not very reliable for alkanes. Okay, so but most organic compounds, including alkanes, alkenes, and alkynes, they absorb a lot from this infrared spectroscopy. Now, the infrared wave is able to affect the vibrational energy, the vibration and rotation of the molecules, the atoms, the vibration and rotation of the atoms in that organic compound. That's why this guy works well. He's able to affect the vibration and rotation. So and once the infrared wave touches the chemical, it begins to vibrate or rotate at different frequencies. Okay, and the frequency at which it rotates actually depends on 3 things, which are the mass of the atoms that are attached and the strength of, okay, so let me mention them. The amount of vibration that it experiences, the frequency at which it vibrates, or how much rotation occurs. The vibration force which determines the frequency depends on the strength first of the bond, the strength of the bond that holds the atoms together, then the mass of the atom as well. The mass of the atom, okay? So for larger atoms, the vibration, it needs higher distance for it to vibrate faster, right? While for the rotation is that it affects depends on the geometry of the atom. The geometry of the atom. Okay, so that there are two types of the geometry that it forms vibrationally. There are two types of geometry that it affects. By vibration, we call them the stretching vibration and the bending vibration. Yes, I remember now. The stretching vibration. And this vibration, what it basically does is that it causes molecules, the bond, to either increase increase in length a little bit, or with that means the atom will move farther away from each other, or will reduce in length, which means that the vibration will cause them to move closer to each other, or the bending vibration. Okay, and this one is just the kink that you see in the molecule. Okay, the kink that you see in the molecule. So keeping in mind the Vesper theorem, so it's going to distort the Vesper orientation of the molecule. Okay, and I've said if you want to you do a video on the Vesper theorem, do also subscribe to the channel and tell me in the comment section. All right, so these are the properties that it affects. Okay, so the IR is more reliable because most organic compounds, absorb of this spectrum. Is that okay? They absorb significant amounts to be able to determine their structures. And because most organic compounds have different types of atoms, or at least different geometry or orientation in space, their IR, when I was talking about fingerprints, the IR spectrum is called their fingerprint. Okay, the IR spectrum of each organic compound is different. Okay, except though for enantiomers. Only enantiomers show. Only enantiomers can show possibility of some similarity in the shape of the spectrum that is formed. Okay, and usually it is usually it is usually since the enantiomers have non-superimposable mirror images, right? So the absorption spectrum also shows that non-superimposable mirror spectrum. Okay, so basically that's it. So it means that the IR spectrum is unique for every organic compound. So this will be it for this video. I hope I've covered most of what you need to know. Then if I need to make a video on NMR, you can mention in the comment section, then I'll talk about it. Basically, I wanted to talk about this, and this is very important. So do want to subscribe to the channel and click the bell notification. God bless you, and share the video with your friend.